Welcome to MEI Numerical Methods, Solution of Equations 1. In this video we'll be looking at the secant method. One of the drawbacks of the Newton-Raphson method is that it relies on differentiation, so that if programmed into a computer, the computer would have to have a differentiation routine. And in the secant method we get around this by approximating the tangent to the curve by a chord passing through these 2 points here. So we choose two values initially instead of the one that we have for the Newton-Raphson method. So we choose x0 and x1 so that they're fairly close to the true root where the curve intersects the x-axis. And we'll demonstrate in a moment that we come up with a new value, x2, which is nearer to the where the curve crosses the x-axis than either x0 or x1. Now the secant method is actually mathematically equivalent to the method of false position. So instead of having a and b as in the formula here, we've got x0 and x1. There's one big difference in that in the method of false position we have a change of sign, whereas we don't for the secant method, which means we're extrapolating rather than interpolating. So the x2 turns out to be outside the interval from x1 to x0, but otherwise it's mathematically the same. So we can prove the formula for the secant method in the same way as we did for the method of false position. And over on the right here we've got a triangle extracted from the diagram on the previous slide, and we're going to use the large triangle and also the triangle at the top. It's also possible alternatively to use this little triangle in the bottom left hand corner. But if we take the big triangle, which has got base x0 minus x2 and height f of x0, and then corresponding sides for the triangle at the top are going to be its base x0 minus x1 and its height f of x0 minus f of x1, and we're trying to make x2 the subject, so if we multiply by minus 1 on this side whilst also multiplying both sides by f of x0, and then we're going to need to multiply the right hand side by minus 1 as well, and we'll do that by swapping the terms on the denominator, so that will give us eventually give us the required formula where we want f of x1 minus f of x0 on the bottom. And then adding x0 to both sides and then putting that over the denominator of f of x1 minus f of x0. And then we see that a couple of the terms in the square bracket cancel out, and leaving us with the formula up at the top. So the secant formula gives us x2 in terms of x0 and x1, and to obtain the next term, the sequence x3, it's exactly the same formula but with x1 replacing x0 and x2 replacing x1, and so on for later terms. Now we'll just have a quick look at an alternative proof of the secant method formula, which is derived from the Newton-Raphson formula. So that's the Newton-Raphson formula there, and we're going to approximate f dash x1 by using a chord from that point to that point. So that chord is approximately the tangent to the curve at x1, and that's going to be the gradient of that chord. So the distance up is fx0 minus f of x1, and the distance along is x0 minus x1. So we see that our formula here becomes this new formula here, with the derivative on the bottom being replaced by that approximate value, and then multiplying top and bottom by x0 minus x1 in the second term gives us that. And then for the x1 term, putting that over the denominator of x0, f of x0 minus f of x1, that gives us those two terms there, and then a couple of those terms cancel, giving us the required formula. So we can apply the secant method to the example that we've been looking at for the other methods. So we've got x cubed minus x minus 1 equals 0 is the equation we're trying to solve, and we need two starting points for the secant method. So if we have x0 equals 2 and x1 equals 1.5, and you might like to pause the video and have a go at this yourself using a spreadsheet perhaps. And here up here we've got the formula which appears in cell A6, and in blue below I've obviously just brought this in, it's not actually part of the spreadsheet. We've got the formula that we've just been looking at, so you might like to compare the cell references with the x's, and you should be able to see a correspondence between those. So for example, instead of x0 here, well, x0 is just our value of 2, so that's A4. Got the A4 there. F of x1 was 1.5, so f of x1 is cell B5 up there, and then x1 is 1.5, which is A5 up there. F of x0 is that 5 there, which is in cell B4, and so on. So we can see that we get down to the familiar 1.324718 after just a few lines, but it's just slightly slower than the Newton-Raphson method, but an improvement on the other methods. So that concludes the video on the secant method.